In section 11.6 of chapter 11, we get introduced to the concept of pH, the pH scale, and how to do pH calculations. So let's begin with a discussion of pH and what it is. Most of us have heard the term before, even before we were in a science class, and many understand that it has something to do with acidity. pH is a convenient method of expressing what the hydronium ion or what the hydrogen ion concentration is of a solution. Remember that hydrogen ion is a shortcut representation for the hydronium ion, and it is the hydronium ion, or hydrogen ion for short, that carries the acidic properties of a solution. An acid solution would have an excess of hydronium ion. Mathematical definition of pH is that pH is the negative log of the hydronium ion concentration, or with the shortcut representation for hydronium, pH is the negative log of the hydrogen ion concentration. So when you're expressing a pH, you are giving a very quick representation of what the concentration of hydrogen ion is in solution. Log numbers, as you may recall, are numbers that you raise 10 to the power of. So easy illustration, what is the log of 100? The log of 100 is 2. 10 raised to the second power, 10 squared, would be equal to 100. So log numbers, just a quick reminder, are numbers that you raise 10 to the power of. We looked at the self-ionization of water and learned that in pure water, the hydrogen or hydronium ion concentration is 1 times 10 to the minus 7 molar. So using the mathematical definition of pH, pH of pure water would be the negative log of 1 times 10 to the minus 7 molar. Now how do you do that operation on your calculator? It can be pretty easy to see that the answer is 7. 10 is raised to the power of negative 7, but it's a negative log, which makes it a positive 7. But even if that wasn't obvious, the calculator will do this calculation for you. How do you do that? Well, first of all, for this calculator that I'm using, which is a Texas Instrument calculator, on my calculator, I would enter in the number itself in scientific notation, and then I would look for the log button on my calculator, press that. My calculator is showing a negative 7, but it is a negative log. So a negative of a negative makes it a positive, and the pH of pure water is 7, positive 7. So in short, the calculator is doing the hard work for you. All you need to do is know how to operate it. There are 4 important equations used in pH calculations, and we've just looked at the first of them. pH is the negative log of the hydronium or hydrogen ion concentration. Now you can take this equation and rearrange it to solve for the hydronium or hydrogen ion concentration. And if you do, you get the hydrogen ion concentration is equal to 10 raised to the power of negative pH. So pH's are log numbers. We are raising 10 to the negative pH because pH's are negative logs in order to calculate the hydrogen or hydronium ion concentration. While I'm here, I should also specify or indicate that you can use the exact same reasoning with POH. A POH would be the negative log of the hydroxide ion concentration. And you can rearrange this equation and solve for hydroxide. Hydroxide concentration is equal to 10 raised to the negative POH. So these first 2 equations, very closely related to each other, both of them convenient shortcut methods for expressing what the hydronium or hydrogen ion concentration is and what the hydroxide ion concentration is of a solution. The third equation we looked at in the self-ionization of water video, that in pure water, the hydrogen ion concentration times the hydroxide ion concentration, and let's make that negative sign a little more distinct there, is equal to the water dissociation constant value of 1 times 10 to the minus 14. So this third equation we've been introduced to already, and the last equation comes directly from equation number 3. If you take the negative log of this equation, you calculate that pH plus pOH equals 14. So these 4 equations are very useful in doing pH calculations, and we'll illustrate that in a minute. The pH scale ranges from 0 to 14, and as we just calculated, the pH of pure water is 7. Water is a neutral system because you have equal numbers of hydronium and hydroxide ion. So pH 7 is neutral. As you decrease on the pH scale moving to the left, you are moving into the acidic range of solution. The lower the pH number, the more acidic the solution is. As you increase on the pH scale above 7, you are heading into the basic range of the pH scale. The higher the value above 7, the more basic the solution is. So acidic solutions contain an excess of hydronium ion, basic solution, an excess of hydroxide ion. If you look at your textbook at figure 11.4, you'll see the pHs of various common substances listed. You can familiarize yourself with that. I just want to point out that the pH of blood plasma is also shown in figure 11.4. pH of blood plasma 7.4, and blood plasma is highly buffered to keep the pH fairly constant at that value. One other point to mention while we're looking at the pH scale is because the pH scale is a logarithmic scale. So if we had here, and let's move that just a little bit further over, if we had a solution that was pH 3 and another solution that was pH 6, which one is more acidic? Well, obviously the pH 3 solution is more acidic because as we decrease in values below 7 on the pH scale, we are increasing in acidity. So notice that inverse relationship. As the pH numbers are decreasing, the acidity of solution, the concentration of hydronium ion is increasing. So pH 3, more acidic than pH 6, but how much more acidic? Well, the difference between these pH values is 3, but remember, that's a log number. That's a number you raise 10 to. So 10 raised to the third power is equal to 1,000. pH 3 solution is 1,000 times more acidic than pH 6 solution. So also keep in mind that the pH scale is logarithmic. Every time the pH value changes by 1 whole number unit, the actual concentration of hydrogen ion or hydronium ion in solution is changing 10 times. 10 raised to the first power is 10. So every whole number pH unit change correlates to a 10-fold change in the acidity of solution. Let's take a look at how we use the equations on the right that we went through to do various pH calculations. So you will need to have these 4 equations memorized, and you will also need a scientific calculator in order to do these problems. Problem number 1. A solution has a hydronium or hydrogen ion concentration of 6.8 times 10 to the minus 4 molar. What is the pH of the solution? First question. Well, equation number 1 would be very helpful for this part of the calculation. pH is the negative log of the hydrogen or hydronium ion concentration. All we need to do is plug in what the hydrogen ion concentration is. pH is the negative log of 6.8 times 10 to the minus 4 molar. And if we do this operation on our calculator, entering in the 6.8 times 10 to the minus 4 value, locating the log button, pressing it, I have 3.17 on my calculator, negative 3.17, but that negative changes the negative value on the calculator to a positive number. And I will write down 3.17. Now a comment. This concentration has 2 sig figs. It may seem as if I wrote an answer with a sig fig error. I wrote 3.17 down for the value of the pH, but it only has 2 sig figs to it. pHs are log numbers, and only the numbers to the right of the decimal point count as significant digits. So the 1 and the 7 are significant. The 3 value is not. The 3 value correlates with the exponential part of the original hydrogen ion concentration and is not part of the significant digits of the value. So pH of 3.17 has 2 sig figs to it. And before we go to the next part, once we know that the pH is 3.17, we can look at the pH scale and see that this solution is clearly acidic. The hydrogen ion concentration or hydronium ion concentration is greater than hydroxide. Here is the second question. What is the pOH of the solution? Looking at equation number 4, pH plus pOH equals 14 gives us a very fast approach to answering this question, right? Where we know what the pH is from part A, 3.17. So using equation number 4 and subtracting pH from both sides, we solve for the pOH. So pOH is going to equal 14 minus 3.17, and we get a pOH of 10.83, which also has 2 sig figs to it. And the third and last part of this question, what is the hydroxide ion concentration of this solution? Equation number 2, right, can be very helpful to us. In its rearranged form, the hydroxide ion concentration is 10 raised to the negative pOH. So hydroxide ion concentration, 10 to the negative pOH, or 10 raised to the power of negative 10.83. And let's just stop for a minute and discuss how you would do this on your calculator. Calculators are different. My calculator would require me to enter in 10.83 and then make it a negative sign using the change sign function. And then I would need to use the log button, but a second function above it. So if I look on my calculator, my log button has above it a 10 to the x function. So if I do a second function log, I'm raising 10 to whatever number I entered in. So I enter in the 10.83, make it a negative sign, and then do a second function log. And when I do a second function log, I'm raising 10 to the negative 10.83. And when I do that operation and express my answer with 2 sig figs, I have 1.5 times 10 to the minus 11 molar. I'm asked to solve for the hydroxide ion concentration. That should be a molar unit, so I want to make sure I include that. Both pH and pOH are unitless numbers and do not have a unit associated with them. One of the few unitless numbers that are present in chemistry that we have worked with so far. So here is our first pH calculation, and now let's take a look at a second problem to illustrate these equations. This time kind of working backwards. In the first problem I gave you a hydrogen or hydronium ion concentration. In the second problem we're going to start with a pH. A solution has a pH of 9.75. And as soon as I see that pH of 9.75, I can look at the pH scale, see that I have increased past neutral 7 pH, and I am now in the basic range. This is a basic solution where the hydroxide ion concentration is greater than the hydronium or hydrogen ion concentration. So this is a basic solution. A basic solution. Part A. What is the hydrogen ion concentration or hydronium ion concentration of this solution? We're going to use equation 1 in its rearranged form. The hydrogen ion concentration is 10 raised to the negative pH. So plugging in what the pH is, 10 raised to the negative 9.75. So entering in 9.75, making it a negative number with the change sign function or button, and then doing an inverse or second function log calculation. Looking at the calculator, I see with 2 sig figs, 1.8 times 10 to the minus 10 molar. So our pH has 2 sig figs, and we're going to express the hydrogen ion concentration with 2 sig figs. 1.8 times 10 to the minus 10 molar. Now, if you're not sure and a little nervous about, is that right? While that number is still on your screen, just hit the log button and go backwards. And if you hit the log button and change the sign, you get right back to your original pH of 9.75. So it can be a nice double check that you have done the problem correctly. Here is our second question. Part B. What is the hydroxide ion concentration of this solution? Let's go ahead and use equation number 3 in order to solve that. We know that the hydrogen ion concentration times the hydroxide ion concentration is 1 times 10 to the minus 14, or equal to the water dissociation constant. So we just calculated our hydrogen ion concentration in part A. If we know the hydrogen ion concentration, we should be able to solve for the hydroxide ion concentration. All you have to do is divide both sides of this equation by the hydrogen ion concentration to solve for the hydroxide ion concentration. So here we have hydroxide ion concentration is equal to 1 times 10 to the minus 14 divided by the hydrogen ion concentration of 1.8 times 10 to the minus 10 molar. And again, this is one of the few times where units are not included in the setup. And when we do the calculation, 1 exponential 14 minus divided by 1.8 exponential 10 minus, we get 5.6 times 10 to the minus 5 molar. Again, brackets are indicating a molar concentration, so it's important to include that unit. the hydroxide ion concentration equal again to 5.6 times 10 to the minus 5 molar. And the third and last part of the problem, what is the pOH of the solution? Equation number 2, pOH is the negative log of the hydroxide ion concentration. So plugging in that the hydroxide ion concentration we just solved for is 5.6 times 10 to the minus 5 molar, taking the log of that and changing the sign, we get a 4.25 as our pOH. And just a quick double check, our pOH plus our pH should add up to 14. So if we take that calculated value of 4.25 and add it to 9.75, we get a value of 14, a double check that we have done this calculation properly.